difference, a whole number, or the integers 0, 1, 2, 3, etc. The domain of any polynomial consists of all real numbers. Another way to write that would be the domain is the interval from negative infinity to positive infinity. The degree of a polynomial in standard form is given by that whole number n. It's our largest exponent that we'll see in that function. The leading term of a polynomial in standard form is given by that whole term, including that degree n. So a sub n x to the n. A sub n is our coefficient, that real number. X is our variable. And n, as we stated above, is the degree of the polynomial. The other way to define a polynomial is in factor form. Polynomial in factored form is given by the function f of x that we see in that second definition box. A, that constant out front, is a real number again. N, m, and k, which represents the exponents on each one of those factors, are whole numbers again. So again, the integers 0, 1, 2, 3, etc. The domain of any polynomial, like we stated before, is all real numbers, or the interval from negative infinity to positive infinity. If we want to find the degree of a polynomial in factored form, we'll give this as the expression n plus m plus k, since that's how our function is defined. Remember that n, m, all the way to k represents the exponent. So to find the degree of a polynomial in factored form, we have to add up the exponents. The leading term of a polynomial in factored form is given by a times x raised to the power n plus m plus k. So we'll see that it has the same three components of the leading term of a polynomial in standard form. It has that coefficient, that real number a, the variable x, and this expression n plus m plus all the way to k, again, represents the degree of the polynomial. If we read the directions on example 1, it asks us to determine which of the following are polynomial functions. For those that are, state the degree. For those that are not, tell why not. So our first job is to decide if each of the functions given below are polynomial functions. Keep in mind that the polynomial function may be written in standard form or factored form. If a polynomial is written in standard form, we should see individual terms added or subtracted from one another. Each term should have a coefficient a variable, and an exponent. The last term, a sub 0, is just a constant, so we'll see that it won't have x with it. If a polynomial is written in factored form, we'll see factors in parentheses multiplied together with a coefficient out front. So let's look at part A. Part A gives us f of x equals 2/3 minus 3x to the 4th. If this was to represent a polynomial, it would be a polynomial in standard form. We have individual terms being added or subtracted from one another. So let's check out each one of those terms. 2/3 is a coefficient. It is a real number. A real number can be positive or negative. It can be an integer or a fraction or a decimal. So 2/3 is a real number. It is a fraction. The other coefficient we would have is -3. Again, that's a real number. We do have the variable x. And the exponent that we have is 4, and 4 is a whole number. It's 0 or a positive integer. So we do have a polynomial function here. I am going to state off to the side that this is in standard form, just to remind us that we do have to think about which form it was written in. And since we know it's a polynomial in standard form, we know that when we find the degree, we're looking for the largest exponent, and the exponent that we're given here is 4. In part B, we're given f of x equals 3 times the square root of x. Off to the side, I'm going to show you that we can rewrite this function. F of x can be rewritten as 3x to the 1/2 power. Anytime we have x under a radical, we can write it as a fractional exponent. This fractional exponent represents power over root. So when we look at the square root of x, we say x is raised to the first power under the second, or square root. When we look at this function now, f of x equals 3x to the 1/2 power, If this were to represent a polynomial, again, it would be a polynomial in standard form. 3 would represent our coefficient, and that is a real number. We do have a variable, in this case it's x, but our exponent of 1/2 is not a whole number. It is not one of the integers 0, 1, 2, 3, etc. So this is not a polynomial function. To state why not, we can write this a few different ways. You could state that it does have a fractional exponent. You could state that you have x under a radical. Either one of those would be perfectly fine. Note that I'm stating that the radical or the root has x in it. It has the variable inside of it. If we were given a function like f of x equals the square root of 3, that could still represent a polynomial because the square root of 3 is a real number. So if you have a radical with x in it, then we can state that that function does not represent a polynomial because that would result in a fractional exponent. Part C gives us h of x equals x squared minus 2 over x cubed plus 1. Now, to start off, this doesn't look like a polynomial in standard form or factored form. So to help us rewrite this, we can rewrite h of x as the factor, x squared minus 2, times the factor, x cubed plus 1. And we need to raise that to the negative first power. So each one of those factors as is given in h of x squared minus 2, and x cubed plus 1, as I put them in parentheses to create that factor, since there's no exponent technically given, we can understand that that exponent is equal to 1. Now, since I wanted to move that x cubed plus 1 factor up to the numerator to make it look more similar to a polynomial in factored form, since I changed its position, I also have to change the sign of its exponent. So it went from having an exponent of positive 1 to an exponent of negative 1. Now h of x can be compared to a polynomial in factored form, so we can determine whether this is in fact a polynomial or not. We see sets of parentheses being multiplied together. Each one of those sets of parentheses has an exponent on it. That number a up front, since again it's not given to us, we could understand that that number up front could be written as 1. A of 1 is a real number. And when we look at each of the exponents and whatever variable we wanted to assign from it from the definition of a polynomial in factored form, the problem that we run into is that negative 1 is not a whole number. So for h of x, we have to state that we are not given a polynomial function, and I'm going to state the reason here as a negative exponent. In part D, we're given f of x equals 9. Now, we might not think that this is a polynomial since we don't have a variable or an exponent involved, but we can actually rewrite f of x as f of x equals 9 times x to the 0. It's true that we are not given any variable with an exponent, so we can replace it with some variable. I'm going to choose x since we were given the function f of x, and since we weren't given any x's, the exponent should be 0. Now I'm going to remind us of a fact from algebra, and that's that anything raised to the 0 power is equal to 1. So what we really just wrote is 9 times 1. And so we see that we didn't actually change the function we were given to. F of x is in fact equal to 9. But writing it in the form f of x equals 9x to 0 might help us make our determination of whether this is a polynomial function a little bit easier. If f of x represents a polynomial function, it would be a polynomial function in standard form. 9, the coefficient, is a real number. We are given a variable x in this case, and the exponent we're given of 0 now, since we rewrote it, is a whole number. Again, the whole number represents the integers from 0, 1, 2, 3, all the positive integers after. So we do have a polynomial function here. This is a special polynomial called the degree 0 polynomial, or the constant polynomial. So it is a polynomial, and the degree, which represents that highest exponent since it's written in standard form, happens to be 0 here. So the degree 0 polynomial, or the constant polynomial. In part E, we're given g of x equals 5x to the negative 3 plus 4. If this did represent a polynomial function, it would be written in standard form. We have individual terms added or subtracted from one another. 5 and 4 would represent the coefficients. They are both real numbers. We have a variable given to us in this case as x. The issue that we run into is that exponent of negative 3. We're going to run into the same issue that we saw in part C. We just didn't have to rewrite it this time. So we do not have a polynomial here, again, because we have a negative exponent. Alright, and then the last part, part F, k of x is defined as x times x minus 2. To help us see and compare this a little bit easier to factored form, I'm going to rewrite this as k of x equals x minus 0 times x minus 2. X minus 0 is equal to x. So we did not change the original function, we just rewrote it. Now we can more easily compare this to a polynomial in factored form. We weren't specifically given a coefficient up front, so again we can assume that that coefficient up front is equal to 1. We have individual factors being multiplied together. We have the variable x. And as we stated in part C, if the exponent on those factors is not given, we can understand those exponents to be 1. 1 on each of those factors, as the exponent does represent a whole number, so we can say that this is a polynomial. I'm going to remind us here that this is in factored form. And to find the degree of a polynomial in factored form, we remember that we have to add up the exponents. So we have the exponents of 1 from the factor x, and we have the exponent of 1 from the factor x minus 2. And so the degree of this polynomial when we add those exponents together is 2.